This video is going to provide a walkthrough for machine learning approaches to best subset regression and forward and backward stepwise regression. We'll start by opening the regression subset stepwise notebook. The key new functions we're going to discuss in this notebook are least squares, which is a fast way to run least squares. This is faster than using OLS from stats models, and so is useful when we're estimating many models and we only care about betas. We'll also look at some methods from Scikitlearn, that is sklearn. We'll look at cross-val score, which is a way to automatically cross-validate a model. Linear regression, which is an implementation of linear regression in Scikit-learn that focuses more on estimation efficiency and prediction rather than on inference and heteroscedasticity and other methods that are better found in stats models. And finally, k-fold, which is a way to customize the cross-validation used when evaluating a model. We'll start by importing NumPy and pandas using their canonical names. The first exercise is to download data from Ken French's website on the valuated market in 12 industry portfolios. We'll use this data here to construct tracking portfolios where we track the return on the valuated market using one or more of the industry portfolio returns. Ideally, we'll find a linear combination of industry portfolio returns that have a return that's exactly equal to the valuated market. In practice, of course, that's not possible. And so in the end, we'll end up looking for a linear combination of portfolio returns, which is of course a portfolio itself, that tracks the valuated market as closely as possible. And the sense that we'll think of closely as possible here will be in the squared error sense. This, of course, makes this a least squares problem, which means we can use many of the tools of least squares to estimate optimal portfolio weights. And ultimately, we can evaluate these optimal portfolio weights to see if they perform well out of sample. The data has been downloaded from Ken French's website and saved as CSV files. The files have been slightly cleaned up, although they're very similar to what was originally downloaded. They have two columns, date and valuated market. The date is simply a number, that is year then month. If we look at the 12 industry portfolios, we can see these are similar with date and then the names of the 12 industry portfolios. Returns are measured as percentage returns, which we can see since the values here are often substantially larger than 1, sometimes as high as 10 or even 20. Returning to the notebook, we see that we can import this data using the usual read CSV command. We start by importing the valuated market, and here we set the index column as date. It's not trivial to automatically convert the date using read CSV, and so the simplest way to convert the dates in this file, which again are year, month, but have no day attached, is to use the function toDateTime that's available from pandas. And here we set the index equal to the index converted by toDateTime, where we give it the format. The format of these dates is simply %y, %m, which means that it should interpret the values in the index as year, month, with no separations and no day. We're then going to use a little trick, which is to resample monthly and take the last. This in practice makes very little difference, but what it's going to do is give us a series of dates where we'll have the last day in each month rather than the first. We ended up with the first from the toDateTime command because since the day is missing, pandas had to extrapolate a date, and it chooses the first since it's an obvious, easy choice. Reading the industry data is exactly the same. We use read CSV, set the date column. We then set the index by converting it to a date time using pandas toDateTime. And then finally, we resample it monthly and take the last value. If we want, we can take a look at the industry portfolio. First few observations. We can see it looks very similar to the CSV. We can also see the date column reflects this resampling method, where it has the last day in each month, and these are in fact what the returns track in Ken French's data. The next exercise asks us to use best subset regression along with cross-validation to select a model and estimate a set of weights that tracks the market portfolio as closely as possible. For simplicity of notation, we're simply going to set X equal to the industries from 1980 to 2014, and we're going to set Y equal to the valuated market also from 1980 to 2014. The second command for y, what it does is it pulls out the evaluated market as a single series, and then it subsets that series to have the dates that will match x. We go ahead and define a couple variables t and p, which we'll use later, as the shape of x. T is the number of time series observations, and p is the number of variables available in x. In order to implement best subset regression, we're going to use a convenient tool called combinations that's available in the standard Python module itertools. Combinations does exactly what it says. That is, it's going to let us choose a set of combinations from a list where we're going to end up with all distinct elements of a particular size. So if we want to get all unique combinations, we need to have all the ones with one element, all the combinations with two elements. Of course, there are quite a few of those since we have 12 columns. All the combinations with three, now it starts getting big, all the way through the upper end where we have, say, combinations of size 10, combinations of 11, and finally combinations of 12, of which there's only one. To do that, we're going to loop over the size of the combinations, which is what we get in the outer loop. We're then going to use this function combinations on the columns of x. This will simply assign to comb each distinct combination of the columns of x with size I. Here we print combination, and as soon as we have a couple, we break for simplicity. As you can imagine, there are many distinct combinations we'd have here. It's approximately 4,000. To implement best subset regression, we need to do two things. For every possible variable size, we need to evaluate all models with that number of variables and choose the model that has the smallest in-sample sum of squared errors. We then need to loop across the variable sizes from 1 until p and choose the best model for each of these distinct sizes. We're going to start by importing least squares from NumPy linalg. Least squares is a faster implementation of least squares than one would get in StatsModels OLS, since it skips a lot of the additional calculations that we need when we want to, say, perform inference on parameters. We're then going to loop from 1 to p plus 1. Remember that range excludes the upper end of the range, and so in fact, this is simply going to be 1, 2, 3, all the way through p inclusive. Inside the loop, we're going to start by defining the best SSE, that is the best SSE we've seen for this particular model size I, as infinity. This is just a trick that means that as soon as we find any model with an SSE that's not infinite, we'll prefer that model. Later, we'll then check if a new model has a lower SSE than the best one seen so far, and we'll keep the model that has the smallest SSE. We're then going to take combinations of the columns of x for each distinct size I. Obviously, when I is 1, we're simply going to look at all the possible combinations that have a single variable. When I is 2, we'll have all the distinct combinations that have two possible variables, and so on. We're then going to take our regressors, which will simply be the x data, which is a data frame, use list of combination. Combination is in fact a tuple. We need to convert it to a list to do proper column selection in a data frame. Data frames interpret tuples different from lists, and so it's important that we have a list here. This gives us our set of regressors. We're then going to estimate the coefficients using the least squares function. The arguments of it are the regressors, or the x data, followed by the y data. This arcond equals none is to silence a warning that NumPy will produce if we don't set this variable. Finally, this bracket 0 at the end of the command means we're only going to keep the first output argument. Least squares returns a number of output arguments, the first of which are the estimated regression coefficients. The others we're not going to need. We then define the residuals as simply y minus the regressors times the beta. Of course, this is matrix algebra, so we use the at symbol. And finally, we can define the sum of squared errors as the inner product of the residuals. In order to find out if we've done better than the best SSE, we simply test whether the current SSE is better than the best. And if it is, we then set the best SSE equal to the SSE, and we retain the best model for size I as the list of variables that was used to produce this model. We then repeat for the next combination, and the next combination, and so on, and each time for a given model size I, we actually find an SSE that's better than the best SSE that we've seen so far. We set the best SSE equal to that value, and we update the model, which is a dictionary of best models. We update the model variables in this dictionary using list comp. This then repeats for the other values of I, for example, I equals 1, 2, 3, all the way through P. And ultimately, what we end up with is a dictionary, best models, with the keys are the number of variables in the model, and the value contained in the dictionary are the list of variable names in that model. For presentation, we simply wrap that in a series so we can take a look at what we get. What we see is that the best model with a single variable is other. The best model with two variables actually is business equipment and money. So in fact, it doesn't include other. The best model with three variables is non-durables, business equipment, and other. So it drops money and returns other. And as we continue to increase the size of the models, we can see that variables are entering and exiting the model in a not totally straightforward way. This is one of the advantages of best subset regression is that it does have the option to drop any variable that it's added previously. This is different from some of the other approaches that we used in the course, such as general to specific or specific to general, where there's path dependence in the selection. One of the reasons why we use the 12 industry portfolios is computational limits. As you can imagine, running this cell doesn't take too much time because we have 12 variables, which gives us around 4,000 models. If we had, say, 20 variables, we would have around 1,000,000 models, and it would take substantially longer to run this cell than it would. If we had 30 variables, it would be essentially impossible to ever have this notebook complete, and so best subset regression is severely limited when the number of variables is large and you have to use one of the other methods, such as forward or backward stepwise, or shrinkage, or trees. In order to complete the selection of the best subset model, we need to then take the P models that we found in the first step, cross-validate them, and find the model that produces the smallest cross-validated sum of squared errors. Here, we're going to define our own function to do the cross-validation. Later, we'll see how we can use Scikitlearn to do the same thing using a single function. We're going to use a function here to do the cross-validation because we're going to use this function many times. The inputs to the cross-validation are simply going to be y and x, that is the actual y data, the actual x data. Then we have a couple additional inputs that I put in just for good measure, which is random, which is going to determine whether we randomly reorder the data that we include in the folds, or whether we're just going to use them in the order they appear. By default, we simply would use them in the order they appear. So for example, if I had 100 elements, the first fold would exclude elements 1 through 20. The second fold would exclude elements 21 through 40, and so on until I finish the 5 folds. If I randomize this, I'm essentially going to reorder the data and then still use observations 1 to 20. But because I've randomly reordered it, that is, I've scrambled the initial order, it's as if I randomly select 20 in each block and ensure that I never overlap. So we start by calling asArray on y and x. This is a simplification. It just ensures that we have NumPy arrays. We've gotten rid of any of the data frame information. This will just make the code later a little bit simpler. We then get the number of observations in y, which we're going to need to set up the folds. We can see the next block handles the randomness. So if we want to use randomization, we read the seed, and we construct what's called a random generator. We then construct a randomly ordered set of indicators using the function permutation and using arange n. Arange n, of course, is just 0, 1, 2, 3, all the way through n minus 1. And so what this is going to do, it's going to randomly scramble the indices, and then we can simply reorder y and x by these randomly reordered indices that are going to be the values 0 through n minus 1, where each one appears only once. And once this happens, it's as if we can then treat y and x as they're in order, even though they've actually been scrambled. Next, we compute the block size, which is simply n divided by 5. We're going to be a little bit careful later because n over 5 may not be an integer, so we'll have to make sure that we include every observation only once. We also set up the cross-validated sum of squared errors to 0. Next, we loop across the 5 folds, and we construct the start and the end indices. So the start is simply I times the block size. So again, if block was 0, the first one I is going to be 0. If the block size was 20, then the first start will be 0. End is going to be I plus 1 times 20 in that example, in which case it would be, of course, 0 plus 1 times 20, which is just 20. We then round it and then use the integer. We need to select using integers. The round is added to handle the fact that the block size may not be an integer. And even though multiplying, obviously, if we divide by 5 and multiply something by 5, we should get something that's exactly an integer. It's possible, due to numerical error, you could end up with something that's slightly off the integer. And if it turns out to be slightly less, you'll end up losing one observation. By calling round, we ensure that we're always going to have that observation in our data. Once I have the start and end indices, I then can construct the indices that I want to leave out. Here I use a little trick, npr start::end, which is simply a way to construct a vector that goes from start to end, and in fact it's the same as using arange in this case. We then need to figure out the ones that we want to use for estimation, which are going to be the full set from 0 to n-1, except the ones we want to leave out. We can use a function called SetDiff1d, which does exactly what it says. It constructs the set difference between the full set of indices, which are 0 to n, and the block we wish to leave out. So those are what we're going to call include. And then finally, we simply regress x include, which are going to be the rows of x that match the indices in include, and y include, which are again the rows of y that match the indices that are in include. Use the same other arguments here and use the bracket 0 to get the first output, which are just the coefficients. We then compute the residuals between start and end, so y st::en and x st::en. So those are going to be the ones we didn't use in the estimation. And so we simply take y minus x times beta, where we use matrix multiplication. And then finally, we update the SSE with the inner product of these residuals. We then return back to the loop, and we loop across the other 4 blocks, adding the SSE each time. Finally, we return the out-of-sample SSE using the return command. At the bottom of this cell, you can see I've executed this function once for a particular value of y and the columns of x that correspond to the best model with 2 variables. We can see the cross-validated SSE is 771. This is not a number we really want to directly interpret, but we'll use the relative magnitude of this cross-validated SSE to the others when determining what is the actual preferred model from the best subset regression approach. In the next cell, we take a look at randomization. And so randomization previously was false by default. We now set it to true. We don't worry about setting the seed. We just leave it the value that it is, although you could change it if that was necessary. It wouldn't normally be necessary to change the seed. What is important, though, is that we use the same seed each time so that the results are actually reproducible. And we see we get a different number. Previously, we saw the cross-validated SSE was 771. With randomization, it's 750. Both of these are reasonable values, and there's no sense one is right and one is wrong. What really matters ultimately is the order we'll get with different models, and usually it won't make a massive difference whether you use randomization or not, although it can. There is no right choice here, though. It's fine to use randomization. It's also fine to use the data they appear in. There may be some sense you want to use randomization if you worry about the fact the model may not be completely stable. Randomization will tend to prefer models that choose more predictions better that work equally across all time periods. Whereas if you don't randomize, and if there is some change in the model parameters, that is, they're not totally stable, that might show up. I suppose it's an empirical question which one works better, and so one could try both when selecting models. Finally, we want to go ahead and compute the cross-validated sum of squared errors for all of the best subset regression models. So we simply loop across the number of variables in the best subset regression models. These are the keys of the dictionary. We then get the variables, which are going to be best models nvar, that is, that's looking up the key in the dictionary, gives us the list of the variables that are included in the model with size nvar. Those are my x variables. The y is always the same. And we simply run fivefold cross-validation, and we store those results as a dictionary, BSR, SSE, XV for best subset regression, sum of squared errors cross-validated. Finally, we convert that to a series, which is a more useful representation since these are numerical values. We can take a look at which model does the best using the IDX-min. That is, that will actually give us the index of the model that has the smallest sum of squared error. We can see that model has 9 variables. We can then look up the list of variables that are included by taking this value and plugging it into the best models dictionary as the key, and we see that that's the set that we choose. There's no particular sense that this is the best set or not. It's more interesting to take a look at the cross-validated sum of squared errors. We can see that when we choose a small number of variables, say 1, 2, 3, there are large decreases in the cross-validated sum of squared errors. In fact, large decreases continue until about 7 variables. Once you get to 7 variables, it actually gets really flat, and that's a hint that somewhere around 7 is probably the right number. Although we can see here the absolute best happens at 9. We do slightly better at 9. From 7 to 8, things improve. At 9, things also improve. When we get to 10, 11, and 12, things actually get worse. So this is a strong hint that 9 is sort of the sweet spot. This is kind of what we would expect to happen in cross-validation. We'd expect things to get better until we start adding noise variables, in which case things start getting worse. And so that suggests that 9 is the right number, although somewhere between 7 and 12 would probably perform similarly according to this cross-validation criteria. We won't explore combination models, but it might be a good idea here that one could actually consider combining models with anywhere between 7 and 12 variables. We can repeat the same exercise here, where instead of using the deterministic cross-validation, we use randomization. So at the end of the day, this will give us a different model. Hopefully it should be very similar. And so we can see now, instead of picking a model with 9 variables, it actually picks a model with 10 variables. Again, the same pattern is evident here, though. Once we get to sort of around 8, 9, 10 variables, the sum of squared errors is very similar. And, we could have easily, or certainly in a slightly larger sample, you might switch from 10 to 9 or 11. So broadly, these are the same model, but it does show that there's not often a sort of incredibly easy case to make a reliable, robust choice that doesn't depend on whether you randomize or not. But so either the variables with sort of 9 variables or 10 variables would be reasonable choices for the best subset regression. The next assignment asks us to construct a tracking portfolio, this time using forward stepwise regression. Forward stepwise regression is very similar to best subset regression, with the big difference that we must pay attention to the previous model when we add a new variable. The strategy for building a model using forward stepwise regression is very simple. We start with a list of variable names. These will be the column names from the pandas data frame containing the industry portfolio returns. And we start with this list being empty. We're then going to have a loop that's going to loop over all the possible model sizes. And we're going to add a variable each time. Before adding the candidate variables, we construct the list of the variables that are excluded from the model by looping across all the columns that are in X and only including them if they're not on the included list. Obviously, in the first iteration, the excluded will be equal to the included, but after we've included one or more variables, these lists will differ. The actual construction you see here is called a list comprehension, and you can see in the middle it has a for loop, for call in X, and then it does something to call on the left. That is, that's the variable that's actually going to appear in the list when the code is run. But it also has an if condition after the for loop, and so it says call, in other words, column name, call for call in X if call is not included. This is simply a compact syntax, and you could write it as a standard for loop with an if clause, but this is often a little easier to read. We're going to use the same strategy for finding the best model in each iteration. That is, we initialize the best SSE to infinity. We then loop across all the variables that are excluded, and we select a new X to try, which is going to include the included variables plus the new column. Included is a list, And so we can add two lists together. Column is, of course, not a list. Column is a string. So in order to add the column as a list, we need to wrap it by square braces, which makes it a list. And then we use selection, x bracket included, plus the list column. We then construct the beta using least squares. And finally, we get the residuals and compute the SSE. Again, if the SSE is better than the best SSE, then we keep the best SSE. And this time, we simply track the next variable that we're going to add. So next var is equal to call whenever we're better than the best SSE. We then loop across all the columns that are excluded for a particular iteration. And at the end of the loop, we know the best variable to add, which is the next var. And so we add that to the included list using the append method. Now the included list has one more variable. We return to the top of the loop, increase the model size by 1, get the list of excluded, initialize the best SSE, and again loop across all the variables that are excluded. We do this a total of p times, and that will build up the list in order of variables that should be included by forward stepwise regression. We can print this list and see the first variable is other. We know that has to be the case because the best subset regression also chose other when there was one variable. Then business equipment, non-durables, money, and so on. The next step is to cross-validate the models that were selected by forward stepwise regression. Here, we'll use the same strategy. The big difference is, rather than having a dictionary of models, which we needed when we did best subset regression, since each model potentially could be different, we now have a list of variables to include that are ordered, starting from the variable that is included when the model includes only a single variable, then the model with two variables, and so on. And so to implement the cross-validation, all we need to do is to loop across the list of included, select the columns in order. In other words, select only the first column, then the first two columns, then the first three columns, and so on, until we've gone through all of the possible model sizes. And so we have a simple loop here that does that. We call cross-validation fivefold with y and then x, where we only include the included columns up to I. We store that value in a dictionary, and then finally we convert that dictionary to a series. We can take a look at the model selected. We see it has 9 variables. We can also see the variables by simply looking at included up to 9. And what we'll see is this list is in fact exactly the same as the list we had when we used best subset regression. This can happen, especially when the preferred model is relatively large compared to the total number of variables. The next exercise asks us to repeat this previous exercise, only using backward rather than forward stepwise regression. The algorithm is very similar. The big difference is that we initialize the algorithm with the full set of variables in the included model, and then we're going to track the variables that we remove one at a time, so that, for example, we'll start with no removed models for the model that includes everything, and then we'll figure out which variable we should drop from the full set of included models, and that'll be our first removed variable. Obviously, the model that we retain then will be all of the variables except the removed variable, and so on. So to start, we're going to start by looping across the possible range of variables, which we know is p. We're going to use the same device here. We're going to set the best SSE equal to infinity. We're then going to loop across all of the variables that are included. We're then going to remove one column at a time. This happens in 2 lines. You can see the first line, try call equals included with a colon. The colon is a simple way to copy a list. This creates a fresh copy of the list so that we're not actually going to change included. We then remove call from the try call list. And then we get the x that we're going to use, just simply using x and then selecting the columns try call. The next 3 steps are the same: estimate the regression, compute the residuals, and finally compute the SSE. And if the SSE is less than the best SSE, that is, we want the SSE that is as small as possible, given a particular number of variables, update the best SSE, and we update the variable that's going to be the next variable to drop, which is going to be call. The idea here is we want to get the smallest SSE, and the one that happens to have the smallest SSE, that is the variable that we removed that produced the smallest SSE, is the next variable to drop. We loop across all of the columns, and then finally, the variable that comes out of that will be added to the removed list. And there's one additional step here, which is we need to remove the same variable from the included because it's no longer a candidate for removal in the next step. We then go back to the beginning of the loop, now with a slightly smaller list of included. We then loop across that smaller list of included, find the variable that produces the smallest increase in the SSE, which is ultimately what this algorithm does, remove that, and so on. We can take a look at the bottom where we've printed the removed columns. And remember, these are in order. So the first variable to remove was durables. Next was chemicals, utilities, and so on. The very last one was money. This is again slightly different than we saw before. Previously, we saw the first variable to enter the model when you start from a small model was other. Now we see the first variable you'd have if you had a variable with one model is money. The reason why it's not other is that other is dropped earlier in the search. So this is a case where at least some of the models we get from backward stepwise regression would not be the same as we get from best subset. Of course, that doesn't mean we won't select the same model ultimately. To finish the algorithm, we need to do the same thing. That is, we simply need to cross-validate all of the specifications that are possible. And here, again, we're going to use a simple trick or a simple device. We're going to simply realize that the included list is just the reverse of the removed list. And so we simply take removed : ::1, which is the way we can reverse the order of a list, and that gives us the included. And so in fact, the code here is exactly the same as the code we used in forward stepwise regression to cross-validate the models. We run that code, and we see that again, we selected a model with 9 variables. The order of the variables is of course different, but one thing you might notice as well is the cross-validated SSE, 204.36, is identical, and that's because the model selected, even though the columns are in different order, is of course identical in the sense it produces the same fit. OLS doesn't care about the order of columns, and so we get the same fit whether we have them in this order or the order that we previously discovered. The next exercise asks us to use Scikitlearn to cross-validate the backwards stepwise selected models. So we're not going to actually rerun the backwards stepwise procedure. We're simply going to remember the fact that we stored each of the models in a dictionary, and then we're going to use the tools available in Scikitlearn to perform the cross-validation. This is ultimately going to lead to a simpler method of cross-validation. In particular, we don't need to write our own cross-validation routine. We can simply use this function crossValScore to cross-validate the model. So we're going to start by importing 3 things: crossValScore, which is imported from sklearn model selection, linear regression, which is available in sklearn linear model, and kfold, which we'll use a bit later, which is available in sklearn model selection. To start, we're going to use the linear regression that comes from Scikitlearn, which has a particular structure that's understood by all of the other functions in Scikitlearn. So we're going to initialize a linear regression, and the only thing it takes, it doesn't take data yet, the only thing it takes are configuration options, and the one configuration option we want is to tell it to not to fit the intercept. That is, don't include a constant. We're going to actually control that here because portfolio tracking models generally should not have constants. They should simply have the returns that we're using to track, because we want to get actual portfolio weights out. We don't want to have a sort of extra value here that we're not exactly sure what to do or how to think about. Again, we're going to use the same strategy here, which is we're going to define BSR MSE CV as an empty dictionary, and then we're simply going to loop across the number of variables in the model from 1 to p+1. We get the included x by taking x and then referencing best models, which is a dictionary, and then looking up value I of that dictionary, which returns a list of variable names. We then use this function crossValScore, which takes a few arguments. Let's talk about the arguments in order. The first is the estimator. So the estimator here is a linear regression. So the first input is going to be LR, which is the model we initiated earlier, which does not include an intercept. The second input are the x values, so in this case included x. The third values are the y values, which is just y. And then here we're using an optional value, which is called scoring, which tells it to use scoring using the negative mean square error. The cross-validation Scikit-Learn prefers to find the largest value, and so it uses negative mean square error instead of SSE. Negative mean square error is very closely related to SSE, and in fact, one can simply multiply negative mean square error by minus t, where t is the sample size, to recover the SSE. What this is going to return, it's going to return a vector of mean square errors, one for each of the folds that it uses. By default, this implements 5-fold cross-validation with no randomization. And so it will return 5 values. And so finally, we call the mean function on those 5 values to get the average negative mean square error. And then we store these. So we can store these, and we can take a look at the values we get. And we can see that the largest value occurs with 9 variables selected. Obviously, has a different numerical value, but we only care about the largest value here. We don't actually care about the numerical values of them. And so it suggests that, again, 9 is the right number, which is what we found earlier. And of course, the model selected is exactly the same. We can actually reverse the transformation by simply taking our values we had previously, multiplying them by minus t, where t is the sample size, and taking a look at this alternative SSE. And look at number 9, we can see it's again 204.36. That's the exact same value we saw before, which is a proof that Scikit-Learn is in fact doing the exact same thing that we were doing before, just uses a transformation of the statistic. Ultimately, this is much simpler to use than it is to write your own cross-validation function, and in general, it's a good idea to use the Scikit-Learn functions when available. The one downside of it, of course, is that we have to use Scikit-Learn methods that have a particular structure. In particular, these models like linear regression, they use a number of function names. So they use a function called fit to estimate the model. Then they use a function called predict to predict values for a different value. So internally, what cross-val score is doing is it's fitting the model on the subset. So 4 of the 5 folds, it's using the data in 4 of the 5 folds each time. It's then predicting the y values for the fold that we left out, and then computing the sum of squared errors from that, and then finally the negative mean square error. The next assignment asks us to do the same task, only using randomization within each block. This is similar to what we talked about before. The way we need to do that here is we need to do a little bit more work. We can't rely on simply letting cross-val score do the cross-validation for us. We need to pass it a cross-validation method that has some options. We're going to use k-fold here. And in particular, we're going to simply initialize the linear regression the same way. We're going to initialize the dictionary to hold the values the same way. But the one thing that's going to be different is we're going to initialize our own custom cross-validation method. In this case, it's going to be k-fold. We're going to use 5 folds, which is what we did before. We're then going to pass 2 additional arguments. Shuffle equals true. That's going to add the randomization. Then we're going to pass a random state value, which is like a seed value. This will ensure that even though it's random, it will be deterministic if we were to rerun this cell multiple times. The only change we have now in the code below is that we pass CV equals CV. That is, we need to pass our own custom cross-validation method. Everything else remains exactly the same. And so finally, we run the code and we see below, we see the negative mean square errors. Again, they're slightly different. And in fact, the selected model is again slightly different. The maximum K occurs with 11 variables. It has a slightly higher negative MSE than we saw before. Before it was minus 0.4 and change. Now it's minus 0.036. Again, this is due to the randomization. There's no sense that this is right or wrong. It's just an alternative model. We do get a sense by looking at the negative mean square errors that any choice between sort of 8 and about 12 perform quite similarly, or maybe 9 and 11. In this case, we ended up with 11. This is common when you use randomization. You might find that you choose a slightly different model depending on the random seed or other things. This is a hint that all of the models are reasonable models. And again, it's a little bit beyond the scope of this course, but model averaging would be a reasonable approach to deal with the fact that you're not totally sure which of these you should choose. So you might say, take the average prediction that you might get with 9 variables, 10 variables, and 11 variables. In general, one would think that's likely to outperform using any of the single models. The next exercise asks us to take a look at the out-of-sample performance based on the models we selected using the different procedures. It's pretty simple to do this. The key here is we want to use the beta that we got in sample and then apply that beta to construct residuals out of sample. So we start by constructing a Y out of sample, which is simply going to be data from 2015 until the end of the sample, an X out of sample, which is going to be the industry portfolio returns, also from 2015 until the end. We then construct the beta using the in-sample best model. So in other words, X and then the BSR model and Y. These are the in-sample values. Retain that beta. We then construct the predictions, which are the out-of-sample X's times beta. Again, we select only the columns that we need from the out-of-sample X's. That's why it's XOOS, and then brackets BSR model. Finally, we construct the out-of-sample residuals using the out-of-sample Y values minus the prediction. And finally, we get the out-of-sample OSS as the inner product of out-of-sample residuals. We can print this value, and we see we get 22.39. This is a value that we'll be able to compare to some results we get in later lessons. This is not a terrible prediction value, but in fact, this can be improved. We can repeat the same thing for forward and backward, and it turns out that it makes little difference. The reason why it makes little difference here, in fact, no difference at all, is that all three of these methods end up choosing the exact same models, 9 variables, and in fact, the exact same 9 variables. This won't always be the case, and in particular, when you have a larger set of portfolios to use in a tracking exercise, you'll normally end up with different models, if for no other reason that you'll have to limit the maximum number of variables you consider in best subset regression to be something modest, say 15, maybe 20 if you're patient, but you won't be able to go up to, say, 30 or 40 variables, which might be available. The next exercise asks us to compute the out-of-sample R-squared for the selected models. So the out-of-sample R-squared is defined as the out-of-sample SSE, which we previously computed, to the out-of-sample TSS. The only thing that's really different here is we need to compute the out-of-sample TSS using the in-sample mean, but no in-sample X data. So in other words, we would demean TSS. However, the model we're fitting here has no constant, and so the TSS out of sample is simply the sum of squared values of the Y out of sample. This is a measure called out of sample R-squared. It's similar to an R-squared, except it doesn't always have to be positive. It can be negative. If you have a very bad model, you can end up with an actually doing worse out of sample with a predicted beta than you are with a beta of 0. So essentially what we're doing is we're comparing the fit of a model with the beta that we have to the fit of a model that had all of the betas required to be 0. Of course, that model has no variables, which again is why the TSS is simply the sum of squared values of the Y out of sample. So you can see we start by computing the out of sample TSS by squaring the out of sample Ys and summing them. We then compute the out of sample R-squared very similarly as 1 minus the out of sample SSE, which we previously computed, divided by the out of sample TSS. And we see that the out of sample R-squared is 98.4%. So in other words, there's about 1.6% of the variation in Y that we don't track correctly out of sample. For comparison, we'll simply use OLS from stats models to get the R-squared in sample using only the out of sample data. So in other words, we're going to take the same data that we just evaluated, the out of sample R-squared, and are going to evaluate that using the parameters estimated on the same data. Of course, this will maximize the R-squared. That's one of the properties we get for OLS, is OLS minimizes the sum of squared errors, which also maximizes the R-squared. And so we can compute the R-squared here, in which case we see the in-sample R-squared is 99.9%. So this difference, of course, is possibly overfitting. It's definitely the case that we know the order of these two R-squareds. It must be the case that the out-of-sample R-squared has to be worse than the in-sample R-squared. But it's always worth taking a look at this. It does give us a measure of how much our model's overfitting the data, and so it's a useful exercise to conduct. The final exercise introduces some of the tools from Scikitlearn, but how we actually use Scikitlearn models. So it asks us to take Scikitlearn's linear regression to estimate in-sample parameters and then produce out-of-sample predictions. So again, we're going to use the linear regression command, and we start by initializing linear regression with fit intercept equals false. We're then going to call the fit method on linear regression with our in-sample data. In other words, X, BSR model, which are the columns that were selected by the best subset regression, and Y. This is going to do what we call in the machine learning literature as training the model. So the linear regression model will remember the parameters. We're not actually going to ever see the parameters when we do this. It will remember them for us. And so this is a trained model, which we can then use to make predictions when we use a different set of X's, although we, of course, need to include the same number of columns in the same location. But that's simple, because when we want to make predictions, we use the predict method, and then we pass it our out-of-sample data. So in other words, we do LR predict with XOOS, and then again, make sure we select the right columns with BSR model. This produces a set of predictions. We could then simply compute the out-of-sample residuals as the out-of-sample Y minus the predictions. Take this out-of-sample sum of squared errors as the inner product of those out-of-sample residuals, and take a look at it. We see we get 22.39. This is exactly the same value we saw above, where we did things ourselves. So, while it's not exactly a goal to learn Scikit-Learn in incredible detail, when it comes to making predictions and simplifying code to make predictions, the Scikit-Learn methods are incredibly useful. And in a future lesson, we'll also see how we'll use these when we do, for example, ridge regression or lasso.